Hello everybody, Mr. Gomez here, and today we're going to be talking about electromagnetic radiation. I have two purposes of this. One, I want to get you prepared to analyze how electromagnetic radiation affects human health for your first project. And secondly, I want to convince to you that electromagnetic radiation, light for example, is a wave. So again, we said we were going to look at how electromagnetic radiation, light for example, is a wave. Later on, we'll look at how it's actually also thought of as a particle in topic 4, quantum mechanics. But first we got to get out the fact of what is a wave. Well, a wave is a disturbance through space. It is regular rhythmic disturbance through space that results in a transfer of energy. It's often thought that waves transfer matter. Think of ocean waves, of which we're probably all familiar. But ocean waves don't really transfer matter, they only transfer energy. So you could think of the wave at a stadium, where a bunch of people will stand up periodically and then sit back down, and the wave propagates around the stadium. Well, no one ever changes seats. They only transfer energy as they stand up and sit back down. And so that's an important way to think of waves. And there's a lot of waves that we've interacted with. There's sound waves, ocean waves, water waves, earthquake waves, and of course electromagnetic waves, or light, and X-rays, radio waves, etc. So we're going to focus on those electromagnetic waves for today. Now there are two common classifications we have for waves, and these depend on the direction of the wave's oscillation relative to the direction of its movement. So if we have a wave oscillating up and down, while moving either right or left, we call it a transverse wave because the oscillation is perpendicular to the movement. If the oscillation is parallel to the movement, then we call that a longitudinal wave. So since we're looking at only electromagnetic radiation, we're going to stick in the transverse wave world, which is probably the more familiar. So what are some measurements we can make about waves? Well, we've all probably seen a wave before, if nowhere else in math class. See, this is a sine wave here, but it resembles the waves that we see in reality. So, just getting some vocabulary out there, the maximum height of the wave is called the peak. The minimum height is called the trough. So if we wanted to measure the amplitude, for example, we would have to draw in our heads the line that would cut the wave in half so that half of it is on top and half of it is on bottom. If you're thinking of this as a standard sine wave, you could think of that as the x-axis. And we'd measure the amplitude from that equilibrium position, the halfway point, up to the peak. Another common measurement we want to make is the wavelength. The wavelength is the length of one complete cycle of the wave. So this is often measured peak to peak or trough to trough because those distances represent one complete cycle. Moving from the peak back to the peak is one cycle of the wave. So it's important to note that you can measure wavelength from any point along the wave as long as you travel that one full cycle. In the last slide, we were really concerned with how the wave occupied space because we were measuring its height and its length. Now we're concerned with how it occupies time. And that brings us to two new measurements, the frequency and the period. The frequency is defined by how many cycles of the wave pass per 1 second. So here we see that this wave is defined to go this many periods in 1 second. So therefore you'd say it has a frequency of 3. Well, what units, you might ask? And the units are hertz. So it's important to note that 1 hertz, abbreviated Hz, is equal to 1 over a second. So it's saying if I have 3 hertz, I have 3 cycles per second. It's kind of an interesting unit. Another way it's written is s to the negative 1. The period, on the other hand, is the time it takes, measured in seconds this time, for the wave to pass 1 cycle. So we come to this mathematical statement where we see that frequency and period are inverse of each other. In other words, the frequency equals 1 over the period. That brings us to the last measurement that we often make about waves, and that's the speed, the rate at which the wave moves through space. So we define speed as v, and speed is equal to the wavelength times the frequency, or you could even say speed is equal to the wavelength times 1 over the period. So this brings us to what is this electromagnetic radiation we've been hearing about? Well, electromagnetic radiation is a very special kind of transverse wave. It's one that we've all interacted with. We interact with every day. It makes up light, radio waves, microwaves, X-rays, infrared waves, ultraviolet rays. There's all sorts of classes of electromagnetic radiation, but all of these waves are principally the same. And they're the same in that they are thought of as oscillating magnetic fields and oscillating electric fields perpendicular to each other. So this diagram kind of shows that nicely. You have these magnetic fields that are oscillating back and forth in the z direction, while you have these electric fields oscillating back and forth in the y direction. The wave, of course, is propagating in the x direction. So, as I just said, electromagnetic radiation is broken into all sorts of classes, but really we just think of it as these perpendicular electric and magnetic fields fluctuating back and forth. This brings us to the electromagnetic spectrum. So we know that the speed of light is constant. It only varies depending on the medium in which it's traveling through, the thing it's traveling through. So the speed of light in a vacuum is defined as 3.0 times 10 to the 8th meters per second. That's wicked fast. In fact, it's the universal speed limit. You cannot ever, and no particle can ever exceed the speed of light. This brings us to the conclusion that the wavelength of electromagnetic radiation is inversely proportional to the frequency. So as the frequency increases, the wavelength is decreasing. As things are happening faster per second, the distance between wave cycles is smaller. And of course, as the wavelength increases, well, the frequency is now decreasing. So we have this idea called the electromagnetic spectrum. It's based on this inverse relationship between frequency and wavelength. Here we can see briefly the electromagnetic spectrum as it moves from biggest wavelength, radio, to microwave, to infrared, to visible, to ultraviolet, to X-rays, and then finally gamma rays at the smallest wavelength. So since the biggest wavelength is over here and it descends going this way, we know that the biggest frequency is over here on the gamma rays side, and it descends moving the opposite way. So highest wavelength, lowest frequency, lowest wavelength, highest frequency. Now, whether we're aware of it or not, we all utilize many types of electromagnetic radiation every day. For example, the radio waves on the long wavelength side of the spectrum help carry information from and to my cell phone and my radios. Microwaves heat up my food. I'm radiating infrared wavelength right now as my body gives off heat. The lights in this room are radiating visible light. But as we get down into the high frequency end of the spectrum, things tend to pick up energy. So the higher the frequency of an electromagnetic wave, the higher the energy it carries. And that brings us to this idea that ultraviolet waves, X-rays, and gamma rays carry enough energy to remove the electrons from atoms. Therefore, they can create ions. So we call ultraviolet, X-rays, and gamma rays ionizing because they have that energy to remove those electrons and create ions. Now, I think it's just kind of cool to stop and appreciate that all of what we perceive as color and light is really only a tiny slice of this electromagnetic spectrum, and that's the visible light spectrum. So here we can see the visible light spectrum cut out from this small inner piece of the electromagnetic spectrum. You'll see that it got flipped from that last slide. But as we go towards purple, we're reducing our wavelength. thus increasing our frequency and increasing our energy. And as we go towards red, we are increasing our wavelength, thus reducing our frequency and reducing our energy. Now, it's also important to note that this is a spectrum. So the boundaries that we have set between, say, ultraviolet and purple and infrared and red are loose boundaries. And so the closer I am to purple light, the more I start to take on the properties of ultraviolet radiation. Conversely, the closer I am to red light, the more I take on the properties of infrared radiation. It's also important to note that this shows us here the wavelength of the light determines the light's color. Lastly, I'll add that the amplitude of the light determines how bright it is. Remember, amplitude being how high does the wave go at its peak. So recall that I'm trying to convince you that light and all of electromagnetic radiation acts as a wave. And so I'm going to take you through some of the behaviors of waves that are applicable not just to electromagnetic radiation, but all waves, and see if you can determine that light does in fact do all of these things. Alright, the first is transmission. Transmission is simply the passing of a wave through a media, and the media is the material that the wave is traveling in. It happens all the time. So here I've got a laser pointer and I'm shining at the wall. I can see the dot from the laser pointer at the wall, but you can't see the beam in between, and that's because the light is being transmitted through the air. This brings us to reflection. Now, reflection is one of the most commonly thought of properties of waves. Reflection is the redirection of a wave as it strikes a new media, a boundary, and then is redirected back into its original media. So we see this almost daily whenever we look in a mirror, but we see it even more frequently than that. And that brings us to the idea of specular reflection versus diffuse reflection. So here I have a mirror and here I have a laser pointer. We can see that if I shine the laser pointer on the mirror, I'm getting part of that light reflected onto the smartboard. So that is true specular reflection. All the light rays are coming in, they're bouncing off, and then they're hitting the smartboard. But you can also see that some portion of the light is left on the mirror and is still visible, and that's because of diffuse reflection. The mirror is not perfectly flat, and so some of the light hitting the mirror is able to be scattered in all directions and sent back to my eyes. This is also why I can see the end of the laser pointer as I shine it on the smartboard, but I can't see it as it transmits through the air. Lastly, I'm going to just put out there a very intuitive concept called the law of reflection, which says that the angle of incidence, and that's the angle between the incident ray and normal, the line perpendicular to the plane of the mirror, will equal the angle of reflection between the reflected ray and normal, that perpendicular line. Basically, the steeper I shine the light in, the steeper the light's going to shine out. It's on the wall over there. But the more shallow I shine the light in, the more shallow the light's going to shine out. Now, I'm trying to convince you that light is a wave, but this isn't a good selling point to me because I've played pool before, and when you play pool, you can see the billiard balls reflect off of the walls of the pool table. So reflection is a property of not only waves but also matter. Now the next behavior of electromagnetic waves I want to talk about is called refraction. We've all probably seen refraction as well. Refraction occurs as a wave enters a new media, so it is not reflected back into the original media, but it enters the new media and thus must change its velocity, and as it changes its velocity, it is bent. The more the wave is bent depends on the wavelength of the wave. So this is the phenomena which is responsible for prisms. So I have a prism here, and you can see that as I shine, without getting myself in the eye, as I shine the laser more or less at that cup of water on the smartboard, the dot shows up over by the prism, and that's because the light is being refracted. Its angle is changing, and it's going farther to the left than you'd expect. A more common example of this would be seeing objects in water. As the light is reflected off the pencil and travels through the water, it must change its speed as it leaves the water and then enters the air. And this causes this bending of the light that makes the pencil appear to look almost broken when I'm looking at it just straight in the air versus through the air and then through the water. And again, we've all probably seen this concept as well. The pencil appears broken. Another very important behavior of electromagnetic waves for us to understand is the behavior of all waves, like the others. And that idea is interference. Interference occurs when waves of the same wavelength combine to create amplitudes either greater or smaller than the waves that went into the combination. So we have two types of interference, the greater and the smaller. Constructive interference occurs when waves are in the same phase, so the crests line up with the crests, the peaks line up with the peaks, and the troughs line up with the troughs, and thus you get a resulting wave that has twice the amplitude of the two waves going into this resulting wave. The opposite is called destructive interference, where the waves are completely out of phase. So if you're completely out of phase, then you have peaks or crests lining up with troughs, and then peaks or crests lining up with troughs. And that means the peak of one wave is able to cancel out with the trough of another wave, and you get a result of no wave. So these two waves can completely destroy one another. This is helpful for when we think about what lasers are. Like what I have here, a laser pointer. So lasers are monochromatic. That means they're only one color and therefore only one wavelength. And they're directed waves of coherent light. So what is coherent light, you might ask? Well, coherent light is arranged so that it is all in phase. And therefore, all of the interference going on in this laser pointer is constructive. I'm adding all of the wavelengths to get just one big wave with the maximum amplitude. And that's why the laser pointer seems so bright. Incoherent light is what comes out of the light bulbs that light up our house. And incoherent light is white, first of all, so it's of many different types of wavelengths, plus it's out of phase, and so it's easier to spread out through the air, and it's not as directed as a laser pointer. So we talked about interference because it's really important in understanding diffraction. Diffraction is probably a less known, by name at least, behavior of a wave, but one we've still all experienced. So diffraction occurs when a wave meets an obstruction, such as an object or a slit, and then bends after the obstruction to fill up those shadowed regions. So what does that mean? Well, you can have sound waves traveling at a door, and then they hit the door, and so some amount of sound waves are able to enter through the door, but then the sound waves are going to bend to fill all those parts of the room that are not directly in the line of sight of the door. Here's another great image of diffraction, where you have a wave coming in, hitting a seawall, but it's able to pour through at this little slit, and once it does, it's going to spread out into more of a circular looking wave. So, this brings us to the idea that if two or more slits are present, diffraction can cause waves that undergo periodic constructive and destructive interference. What these interference patterns look like is going to be, you have your original line coming into two slits, your original line being your wavelength, and those two slits are going to cause the waves to spread out in these semicircle arcs, and where we have perfect constructive interference, thus making bigger amplitudes, we're going to see the semicircles intersecting, and then once it hits a wall, it's going to reflect bright light. And where we have perfect destructive interference is where we don't have these intersections. And then when it hits the wall, we see nothing. It's just the darkness or the color that was reflected from other light sources. So here's an example of diffraction, and we'll use this concept much more later on in labs. But you can see that this diffraction grating, which is a bunch of very small slits, is causing the green light to spread out. So we see the one dot, but we also see dots on either side of it. And those dots are where we've had perfect constructive interference leading up to it. The last behavior of electromagnetic waves I'd like to bring up is called absorption. We've seen absorption all the time, every day. Absorption is when an incoming wave is actually captured by an object, and then its internal energy increases as a result. And so you could think of internal energy as temperature. So black objects are really good at absorption, and this is why black objects exposed to sunlight will heat up so much, because they're capturing all those incoming waves and not letting any reflect back. But perhaps a more interesting example in my mind is the leaf. So when sun shines on a leaf, you have white light coming in, which is really a combination of all the different wavelengths that make up the visible part of the electromagnetic spectrum. And what the leaf does is it captures all the colors except for green. And so the color we perceive as the leaf is actually not the color it's absorbing as itself, but it's the color that it's not accepting and reflecting back to our eye.